Something on Thursday on phone. I found like 50% bruises. Yeah, so my friend threw me on the ground. You don't even want to see the bruise that I have.
Oh, really? Until
Actually, good friend. That's after
last 11:59 I passed it.
I was at Vance and I like we were Vance is bar dance. Yeah.
I'm only taking out 50% of
like bridal set. And I'm like
Come on.
but you know like that before. And so I guess
Okay, let's get started.
she just
Let's see. So homework's due today.
so like I
Timers homework was released and is due next week, and we have office hours today. The more exciting parts for this week are we'll have our team ideation event on Friday. Oh, we don't have the time. I think it's 4:30. Check. But your project ideation slides are due. So there's a Dropbox folder. You just put Google Slides preferably, but you can put anything. You can be PowerPoint if you want. And so you put them in there, and the goal of this assignment is to get you to start thinking about what projects, like have real concrete ideas that you've thought about, not just like, oh yeah, I'll do something. Like come up with a plan, an idea. You might not do it, but at least you're thinking about something. Put a star up in the corner if it's something that you're real excited about and would like to, present to the class or just talk about. We might not get through all of them. I'll take all these, put them in one PowerPoint or one Google Slide presentation and have them available so we can all look at them. Yeah, any questions?
So will we be able to see anything else in ideas?
Yeah.
Like,
You could, it's even worse than that. You know what you could do? You could team up with them and do the project together. What's that? Yes, do it individually. You individually put 3 in, and it's kind of like advertising. If you get real excited, you can scroll through everybody else's, yes?
When do we have to form teams by?
Wednesday next week. Team registration form, yeah.
Just curious, like what happens if you have like 2 full groups in the same idea? Like, is that just like okay?
Yeah, I doubt you're going to do exactly the same thing. We can push you into different technical paths.
How feasible will these 3 ideas after that you turn in?
Reasonably feasible. Like I've had people there like, I want to make the smart AI pen that like interprets your handwriting and corrects your handwriting and talks to you and has a voice interface. And you're like, oh my gosh, like it's pretty far off, right? But don't worry too much about exact feasibility. We'll help you because there's things you don't necessarily know how to do. So we'll help you figure out your ideas, but just don't assume there's general AI. This is going to solve all your problems. Does that answer your question?
And like, what's the simplest you can put?
The simplest?
Yeah.
I don't know what that means.
Like, what's the easiest project?
You want to know what's the minimum effort you can do for the slides or just project in general?
Theoretically, well, for the slides.
Let's see. According to the slides, you need to put less than 100 words. There's not a minimum. So it indicates that there has to be words. They have to have an image. Okay, so you at least got to go to Google and steal an image. You got to put your name on there, and you got to upload them. So I guess that's the minimum. Will be graded as class participation points. Projects, maybe the question is like, what's the minimum project? The goal of the projects is for you to demonstrate knowledge in embedded systems through an open-ended project. We make an open-ended project so you solve real constraints and real-world problems and have to make trade-offs. You will have to demonstrate knowledge of core concepts like interrupts or timers. We'll talk about ADCs and serial peripheral interfaces like UART and SPI and I2C. So there's things that you will do to demonstrate your competency in this class. And then we have somewhat vague, but somewhat rigorous method of just counting up all the little modules, all the pieces that you've done, and assigning you a difficulty score. So your goal is to make the project difficult enough to support the number of people. If you come up with a really simple project for 2 people, that might be enough, but a simple project for 5 people probably isn't going to cut it. You need to each have modules of work. And we'll coach you through what that looks like. There's no hard and fast formula. Any other questions? Okay. So today we're going to finish up, we're talking about timers. Did we get through pulse width modulation last time? You want me to go through the animation again? Yes? Okay, let's do it. Well, before we do that, it might be worthwhile to think about what we're trying to do is to create a pulse that's up for a certain period of time and then low for a certain period of time. You have a period associated with that pulse. And so it could be high all the time. And then you're just putting out a logical 1. That's fine. It could be 0 all the time. That's fine. So that would be a duty cycle of 0% if it's all 0, a duty cycle of 1 if it's all high. But then you have some gradation in here. You have some step size. And so now you can set your pulse width modulation to some other value. And pulse width modulation being a fundamental tool in embedded systems to control the external world in some way. And what you're doing here is usually you're encoding information in terms of time. And microcontrollers are really good at keeping track of time, about the only thing they're inherently good at. And so you can make them really, really fine resolution. And that's a way to control something analog, like the position of a arm or something of a servo. So that's the wordsmithing of what a pulse width modulation is, but we can get an intuitive sense here. So let's see, turn this thing on. Doesn't make much sense. So I have a clock. The clock has variables in it, so I can set, the waveform is the square wave, the min and max, the DC offset, the frequency, and here I have a duty cycle parameter. I'm going to change that parameter over there. So it says 0 to 100 being a percent. And here we get some waveform out the bottom. It looks like this. We can see the LEDs on. All right, so now if I wanted to, you can see that. And so if I wanted to, I can go lower the duty cycle. And now I just have these pulses are shorter in time. And so a lot of the goals with timers is to figure out how do I control the period and the actual amount of time the pulse is going on. And we can increase the duty cycle to any variable in between. And if I make the simulation much faster, I can't really see it on this screen. So let's see. This is how you would dim an LED. So now it looks, oh, it kind of looks good. Now it looks basically on. And you guys can't really tell, but imagine it was blinking very fast, then you would see this thing would be, on time average, would be dimmer. So when you see pulsing LEDs, this is what they're doing. They're almost 99% of the time changing the duty cycle. Let's see if I can trick this machine into making it look good. Nope, there's aliasing between this screen, the refresh rate of my browser, and the refresh rate of that thing to make it look horrible. But does anybody have questions about duty cycle or how you would change the brightness of an LED? Yeah.
So did you say a LED pulses like in different time, have different duty cycles to change the brightness?
Exactly what I'm saying.
Really? Like all?
Yes, really.
So if you turn up the brightness, it just like pulses longer?
Yep. It just happens that humans are pretty slow things. Best, you're like 60 hertz, right, to see something. So they do cycle much, much faster. Your eye can't tell the difference. So to you, this looks like dimming.
I thought it's just put more power into the LED.
What do you mean? What's the word? What do you mean by power? Because the power does put more power into the LED.
I was thinking more like current.
It does put more current in the LED, in fact. But what is it not changing? So this yellow line here is the current. In fact, what you're doing is you're pulsing current into the thing. It's just you're not changing the voltage.
Oh,
because LEDs or digital systems are bad at controlling voltage. That's not what they're digital. They're not analog. And so yes, we're going to talk about analog digital converters, but those are specialized pieces of hardware. They're painful to make. It's much easier to control time. And so if we go very, very fast, you won't notice the difference. Would you agree with that? Is that your intuition said if we blink this at a kilohertz, real kilohertz, not this fancy simulation kilohertz, that you would not be able to see the difference?
Yeah, but
Yeah?
So like if it has a higher frequency, like does it get brighter as a result?
No?
Like how do we know if it's dimmed or like bright?
We'll look at the duty cycle. So think about what's happening here. This is voltage, right? And if the thing has more voltage, if the thing is like this, hold on. Is it on? High voltage, right? Okay. Low voltage, right? Off. Okay. What about there? Half the time, this is about, now let's make it 50%. Half the time it's on, half the time it's off. What's the average of that? 50%, right? So now we're going to say it's 50% of its brightness. Now that doesn't really deal with the IV characteristics of a diode, but that's 215 or something. We're not going to care about that. We're going to say, it's 50% the brightness. Does that make sense? Other questions you have? Well, you guys can play with this in lab. Make LEDs that dim, glow. They're very, very exciting, very satisfying. I'd also point out this is how motors, like almost all DC motors, are going to be controlled, right? Because again, it's very hard to have like, hey, a 12-volt AB quarter-watt motor or something. It's very hard to control 12 volts and, oh, I really want it to be 6 volts because I want it to go half as fast, right? So instead what you do is you put out current pulses, not a constant voltage. So you have a voltage here, and then the yellow right here is the current pulse, so it goes along with it. And then you're just spinning up that motor. It goes a little bit faster, but it's going so fast that you can't see it. It's not that it's going to, it's just going, going, going. It's basically getting a little push every cycle. And it's so fast that, well, you can't see it, and then the inertia of the motor, when there's no voltage applied, is going to keep spinning. So on average, you can control the speed of motors, and you'll do that. I don't know if you do that in lab, but most people end up doing it in a project. Okay. So hopefully that's motivated why making pulse width modulations is a big deal and important. Okay, so we've talked about timers that are going to count up to a certain value, right? And then we're going to overflow in this case, and then go back to 0 and count up. And then we're going to, so that's the first thing we're going to talk about is how to set up times with your STM32. And then we're going to talk about how to do set up the pulses. So first we're just going to set up timers, which is this first part. So in this example, we have a timer. So here is this is time going this way. We have a representation of the counter in a clock. So the clock, every cycle of the clock, I think it's on the positive edge, the timer increments. And here our auto reload counter is set to 6. And that's the counter that's a register we put a value into and says, okay, when that occurs, when you hit that value, reset. And then it's going to go back to 0. What does RCR stands for? Oh yeah, the repetition counter register. So there's another register in there where you can say, I want you to only count 6 times or n times if you wanted to. You just want to have a pulse that goes out 6 times. Lots of reasons you might want to do that. You can tell it how many times that you should do this overflow thing again. But if you set it to 0, then it's just going to go forever. So all these examples just assume that you're going to set up this waveform counting over and over, going forever. Okay. And then this is just showing you here the counter where the underflow event is. And so here, the first goal, we're trying to figure out what's the period that we have here. So we have the auto reload register plus 1 because it's the 0th bit there, times the clock frequency. We didn't specify the clock frequency, but you just say it's this times your clock frequency. So it's 7 plus your clock frequency, or clock period, to figure out your period of your waveform. And so you might want to have a long period or a short period, depending on your application. If you're blinking LEDs, if the period's too long, then the human will start noticing. What's your question? Could be. Okay. What is this transition here? Oh, I took it away. Okay. So you can see better. Any questions about this? So you're going to put some values in the auto reload register. You're going to say 6. Repetition repeat counter is 0. You're going to tell it to be in compare mode. This is not a capture operation. This is all internal. So you're just comparing when 6 equals, when you count up to 6, which equals your auto reload register, then it overflows and goes forward. Okay. If you look at the alternative case, you can always count down. You can set your counter to be counting down mode. You can start at 6 in this case. You count down to 0, and you underflow, start back up again, going back and forth. Here, you'll see that the period is the same, still 7. Okay. We have the other waveforms that we looked at, which is the count up, count down. So sometimes we call it center aligned. And so this is nice in the sense that, say your counter couldn't count up to, at 16 bits wasn't enough time for you. Most of the counters on your STM32 are 16 bits. Well, here, you could do 16 times 2, right? You can get up to, or 16 bits times 2, so you can get up a longer waveform and using this method. So here, if you set up the registers in the correct mode, you'll count up to 6, and then it'll revert, count down from 6 down to 0. So 6 is your auto reload register to 0, and then back up and back down. So here you're getting overflow and underflow events. And here the period is this 2 times your auto reload register times your clock period. Okay, in this case 12. It's a little tricky if you count through all the math. If you do single-sided, it's always 1 plus because you're counting for the 0. But if you do it this way, I don't know, the math comes out different. You have to prove it to yourself. Here, it's just 2 times. There's not a plus 1 here. It's just 2 as you go up and come back down. All right. Any questions about how we'd set up a period? So you can make you get to control things, you can control your clock. If you have a prescaler, you have your auto reload. That's about all you need to know to set up a period. Yeah.
Why do we use both a prescaler and the ARR register?
That's a great question. Why? Anybody have an idea why you'd want to do that? Yeah.
We can the scaler can increase it to a limit that we could not have into the bits that we have in ARR. So if you want to really increase it or amplify it, then you can't store that by default in ARR.
I think what you're saying, I think you got all the right ideas, but maybe you say increase it, you mean increase the time, increase the period, right? Okay, so I have a 100 megahertz clock into 16 bits. That limits how long I can keep track of time for.
Yeah.
But if I slow my clock down, I can go for much longer.
Okay.
Right? And so now you're making this trade-off. You're making a trade-off per precision, right? Because if you go the fastest clock speed, and you want some intermediate value, you want your AR to be something, you can get very, very small ticks. But you might not be able to go very long. So now you can trade off time for resolution, or absolute or longest period for resolution.
Okay, and as a follow-up question, are those variables dependent on us, or can we configure them based on, or do we have to configure them based on a specific requirement for a bus connection, or maybe like a APB bus connection? Like, does the clock period have to match a bus frequency or something, or are those entirely dependent on us?
Maybe. Let me rephrase this a little bit. So yes, the timer is a peripheral module, okay? Mm-hmm. We're not really worrying about how the bus connections come up to it. We've worked on the memory mapped I/O, so we're not going to focus on how we wire up this peripheral. So STM's already done it for us. We talked about the clock tree and how you could clock things a little bit. You'd have control. So if you remember in CubeID, you have this nice GUI that's horrible to read, doesn't make any sense, and you can click buttons and hopefully a clock signal comes out of there if you're lucky. So those clocks you can send to this peripheral for your timer. And so you have different clocking options. Typically, maybe the default case would be it just works off of the APB clock, which is 120 megahertz. I don't know if that's a default configuration, but that's the maximum speed.
Okay.
And then after that, you can pre-scale it down. And then the AAR or the ARR and RCR, those are registers which you could write to. So yes, you are responsible for them, although between the HAL drivers and the GUI interface, some of that's going to be abstracted away from you. Good questions. Any other questions so far? All right, so now you should be able to make, given some clock frequency, and assuming it's a 16-bit timer, you should be able to make a period, a clock that counts up to some period of time. And now we have to go figure out how to do the next piece here, which is actually have a pin, ultimately, sure, a GPIO pin, but here just conceptually, a signal that's going to control when this thing goes high and when the thing goes low. And then you're going to vary this value here as part of your duty cycle. Okay. So now we have our capture compare register. So that was from last lecture. We have auto reload register, the capture compare register. And now we can say when the counter equals some value, do a task. Okay? Before it was just conceptually set up a interrupt service routine, and now your core could do something, sure. But there's another mode where you could just say raise that pin. We don't actually have to go all the way to the core for in an ISR to go and raise a GPIO pin with the store. That is fine. It just it's such a thing would happen so often that STM provides you the capability of raising a GPIO pin off of this signal without going to the core. So it's a little bit of a hardware acceleration in that point of view. So here, what we're going to do is we're going to put a value in our CRC and start counting up. When the counter equals our CRC, then an event occurs. And here we'll have that be, I guess this is the falling edge of our pulse width modulation. So there's different modes. You can have it on the rising edge or the falling edge. You just have to look through your documentation to see those details. Sometimes the math works out a little bit nicer. But here I can control this value. And so this is really, your CRC is a version of your duty cycle. You can make that number smaller in this particular case to have a much smaller duty cycle, or you can go all the way up to 6 and have a high duty cycle. So that's the value that you're going to be controlling. It's just not in terms of duty cycle, it's in terms of counts. And it's your count of your CRC over the entire period. So here, CRC over your auto reload register, because this is just the triangle wave, it's always +1. And so here you can figure out your duty cycle, 3/7. So I'm going to ask you if you have any questions. Yes, fantastic.
The CCR also making the rising edge at 6.
Is the CCR making the rising edge at 6? No, this event is occurring because it overflows. So I should have made that clear. In this mode, you'll set up your counter specifically to make pulse width modulations. And so it's saying here you have an overflow event that takes it back to high, and then it only goes down to low when the CRC equals that. So there's, you go look through your data sheet and you figure out all the little bits to put in the registers to make these configurations. Yeah.
I remember homework 3, we were using like the timer module, and I think it, based on the frequency of the clock and just determine how long it would take, I think it came out to be 4 seconds of real time before it reset. If you want to make clocks that are a lot longer than that, do you layer these? So you say oh, only when this clock gets to reset, then you increment the next one.
You could. So we'll talk about that. The later half of this lecture, we'll talk about virtual timers and how to measure things on scales of years. But yes, there has to be at some point, you'll run out of bits in your timer. And then it's probably going to, software's got to take over to make up for that. Okay, yeah.
Can CCR be 7 to have 100% duty cycle?
I'm sure it can be. I'm trying to remember if there's inherently an error that's going to occur. So if your CCR is higher than your ARR, right, then the event will never occur. I think that's totally fine to set up your thing that way. I don't think you'll get an error, and that way it would just always be 1. Okay. And there's how you figure out the period. So we can go through, oh, this is, what am I showing you here? Oh, this is just the opposite case. You can go set yourself up in the other mode where this is the polarity flip between these two slides. So here, it started off 0 and then it went high. And these are just little details to keep track of as you go through your labs. But and homework will tell you what the orientation would be if it's either inverted or normal rising edge. I will point out that this did change the duty cycle just because here the CCR was 3, so this was up high for 3, down for 4, and then because we inverted the signal, here you're down for 3, up for 4. So that just changed your duty cycle, but that's just a math keeping piece in a sense. This is probably the more interesting thing, kind of alluded to this, but this is here mechanically how you would go and change your duty cycle. You just change your CRC, which is kind of nice that you don't have to go and change up all these registers. If you just want to change your duty cycle, you're just setting one value. You're just changing your CRC, and now your brightness of your LED changes, the speed of your motor changes, or the servo arm position changes. Count up, count down mode. Same thing, it's just now you're doing double, right? So now your equation changes slightly to figure out your duty cycle, and it's over, in this case, it's over 12. So here you're high for 6, low for 6. That's the difference here. And again, you can change your duty cycle. Here we're just changing between 3 and 1 to change the duty cycle. So this is like the toy diagram of your timer register. One thing that's nice is it has multiple capture compare registers. So that means with one, you set up one period, you set up one timer with one period, and then you can have multiple duty cycles that come out of this thing. So you can have maybe you want one LED to be very bright, one servo motor to do this, one whatever it is, or maybe you have multiple servos you want at different angles. You just have to change one value. You just have to make sure that the period you've set up works for everything. Did I see a question over here? Yeah.
Would this not like constrain us to only having 4 different peripherals with different like clocks, right? Like because you can only have 4 different CCRs.
Well, this is just, you have multiple modules on your device. So there's multiple timers. I forget how many on yours. I think there's 17 different timers on your STMs. That number's about right. And then some of them have multiple capture compare registers. So yeah, there is a finite limit on the amount of things that you can control with time. There's also a finite limit on the number of pins. So I don't know, generally it works out. Do you have another question? Okay. If you found yourself in a situation where you had lots and lots and lots of LEDs to control, there's GPIO expanders, there's other hardware mechanisms to be able to control lots of LEDs. So here's an example of just having two, just using that same concept here. Here we have 2 capture compare registers, and they each have different values. So now you have different thresholds. So here you're probably getting around a 50%. This looks like a 1/7 or 6/7 duty cycle. So just showing that, hey, look, you can go and get multiple duty cycles out of one timer. There's a small difference between whether you're left edge aligned, right edge aligned. I don't think that's that important. But it's just something, again, to be aware of in your labs or in when you're making a device or for your projects, is what's your alignment level. Sure. There's one other register this is useful to know about, maybe more from our architectural point of view, and that's the auto load preload register. So there could be a condition where you want to change your duty cycle. But if I change my duty cycle at some random point, you could shorten. Imagine if you're here, and all of a sudden some command comes in and you change your CCR, but you changed it here. This might change just for a short period of time. You might get a glitch in a sense, where you might get the pulse may restart or something, because you were asynchronous. And so if it's an LED, probably doesn't matter, nobody's gonna care, but it could be a control arm for a servo, and all of a sudden you'll get a little glitch or something. So how do you deal with that? Well, the fine folks at STM gave you this preload register that allows you to load a value in there, and when an underflow event or an update event occurs, so this is either overflow or underflow, then it will upload the preload register. So that means that you can synchronously control the duty cycle and update it only on those edge transitions, eliminating glitches. Any questions? Okay. Yep.
Hypothetically, in this example, when you were talking about like, in the case of like a servo or something where it might cause a small glitch, like wouldn't the hertz be going fast enough that it would like only cause a glitch for like a microsecond or something incredibly small that wouldn't actually do anything?
It depends on your application. So an LED, you probably wouldn't notice. The period for servos is usually like 10 milliseconds or something, maybe 50 milliseconds. It's pretty long. So it's possible that you could see a glitch. Is that glitch a real big problem for those applications? I don't know, but we can think of some applications where, I don't know, you're controlling the wing of an airplane or something, right? Maybe you're gonna use something beefier than STM32, I don't know. But there are time-sensitive ones where just having a little bit of glitch could do bad things, and this is just a way to alleviate that. What was I wanted to teach you here? I don't want to teach you anything. I did not give you a complete guide to every aspect of timers and enough to do your project. I gave you the overall high levels, so it's up to you guys to read through the data sheet, understand what's happening. This is the part of the class where we're transitioning from trying to spoon feed everything in the labs to getting you guys to do the exploration. This is a real, I forgot which timer. I think this is the advanced. Yeah, this is the advanced timer control. So this is just showing you what's from your data sheet. And at this point, you can almost read almost everything. So there's some edge input filters if you needed that, pre-scalers, especially if this is coming from off device, capture compare registers, and your output controllers. So, and there's auto reload up there. Pre-scaler, oh, that's from that clock domain. This is if you're doing capture, sorry. This is the capture line. That is the line up there is your clock coming in, capture compare registers. So with a little bit of effort, I think you should probably be able to work your way through most of this diagram. Just telling you what the expectation here is. I'm not going to give you that diagram on exam, even that's horrible. Maybe as a data sheet element, that would be fantastic. But I'm just saying that now you're getting to that point where reading through the data sheet should at least be possible. It should not be too insane. All right, so we'll go through the exercise here of calculating these values. So the goal here is to come up with the PSC, so that's a pre-scaler, the auto reload register, and the capture control register values to create a pulse width modulation, 10% duty cycle and 100 milliseconds. And as you might have guessed, there's going to be multiple answers because you guys get control over some of these variables.
A meeting or another class? No.
The reason I
Okay, I got you. Yep.
And I went to Madison approached for us.
For some reason, like, no, I feel like No, for the midterm.
Irrelevant and 10 meter only.
You guys can work together, I promise.
It's just setting up pulse modulation basically. I missed a lot of things.
All right, and since it was last class we talked, that's the formula for the prescaler. So clock in, clock out, prescale value, and this is the goal. You want something, a period that's 10 milliseconds with a 1 millisecond rising edge.
16 millihertz.
Or rise time.
10 milliseconds. Equals period of 10 milliseconds.
How are you going to start?
What is PSC? Period. It's the frequency of 10 milliseconds. I'm pretty sure it's 100 hertz, right?
No, I think there's auto reload register.
Yeah, what your turn.
I'm trying to get you.
It's like minus 9. Milliseconds only minus 3.
Yeah, yeah.
You got a prescaler.
There's 6 in there.
Thinking like the actual clock cycle has to be 1 millisecond for the equations that are relevant for this.
There's one.
Yeah, so you go all the way from 16 megahertz down to
You need to get a period of 10 milliseconds.
yeah, it's not confusing about two because it's already 16 megahertz, right? I don't remember what it is. 100 hertz.
Okay, cool.
And so, I gotta, what is the CK, what are the subscripts on the?
So we have the,
Well, no, off the top there, how many milliseconds? 1 cycle of a megahertz.
EECS.
This is 10 to the 6 cycles per second.
So that's 1 millisecond.
Each period is 1 over 8 seconds.
1 millisecond.
Yeah.
16. Backwards. Clock prescaler is prior to the prescaling.
Period is 16 seconds.
The frequency was 16 and the maximum. Because you could drive at
Yeah, I think you were, I think it's 0.1.
So is it because it's pre-scaled?
No, but we want to do, oh, we need a different, right?
So duty cycle for this is that.
I feel, I can't remember the last time we did one.
ARR.
What's mute is mute aspect again.
Yeah, we should probably change.
We say.
It's like multiply by 1,000.
Okay. How is CRR is going to reach refreshes, right?
Oh, we don't even define our CR here.
This is 12. And they want to get.
Yeah, that makes sense, actually, makes sense.
Just examples. That was the answer. And we're given 16 megahertz as the thing, so 1 over 16 will be the microsecond.
So make those adjustments in real time.
16, am I crazy? Or is this what it is?
Oh, it's right, it's CCR over.
This should be the clock period,
It has a period of 10 milliseconds.
Choose your ARR? 62.5. Yeah, I guess.
So it's the one period of 10 milliseconds. Yeah, no, you're right. So yeah, so 10,000 milliseconds is equivalent to one period cycle is 1 over 10, 1 over 16, right? Or it's 16 megahertz, 1 over 16 microseconds. 10,000
value that you're gonna
65.
Just like this.
CCR equals 1, AR equals 10.
The prescaler.
Also, literally just take 16 to make one.
Yeah, this graph is not really the problem.
It's just the two values, right? So you have prescaler.
And then we need
6.25 in prescaler, like this.
Oh, yeah, 62.5.
CCR is 1/10 of AR. 90%. It's backwards, yeah.
Say that you might
High true. If you're above the CCR,
yeah.
or just there's one that you said.
PSC is
slow down.
so the duty cycle.
Just this clock?
You can adjust that. Well, you could prescale that clock.
Yeah, it's gonna be a really large number. Okay. I haven't calculated that yet, but.
We got 4 hours.
I think that 9 and 10 and 1 millisecond.
So every time we clock out,
It's 10 milliseconds, so.
because I feel like 1 millisecond.
On this example, the AR, it's like you get to 6 now. This is like what we have to.
Hold on, let's talk about prescalers again, because I feel like that was long time ago.
I'm getting some
Clocks,
I don't know.
this is like your B bus clock, right? Say it's 100 megahertz. That clock may be going so fast that you will get through all 16 bits way faster than you want. It won't give you the period that you want. So they give you this prescaler. The prescaler allows you to divide this clock down to some slower value.
So it has to be 16.
The equation with the poor suffix or the poor subscripts here, which comes from the data sheet, we can change it. Basically just says you take the input clock, you divide it by your prescaler plus 1, because this is a register value. If you put 0 in here, then the clock stops and your whole thing stops working. They don't allow you to do that. It'll get out a slower clock here. So here's how you can manipulate the prescaler, or the clock, or sorry, so you get a 16-bit clock, but that may not give you the resolution or the period that you want to get your job done to get the 1 millisecond pulse that we're looking for. Questions on this? Yeah.
So the two variables are, if they're, that's frequency, right? Yes. Or like the F.
Yeah.
That's frequencies, okay. And clock prescale is after it's been prescaled?
Yeah.
Okay.
No. Oh, I don't know why it's like this. This is the faster clock. So if I just look at the math, I have a fast clock coming in and I divide it by some value. And then the clock dividers, so this was like the divide by 2 dividers, and then this, the prescaler on the SCM is really a 16-bit counter that divides things for you.
AR, we get CCR.
I want to.
This is clock period times AR times 2.
And you know the period of error is not.
The prescaler is just a number that we selected. It takes that.
What you change the whole to achieve this is a period of 1 duty cycle needs to be 10. So that means the duty that it's high for 1.
Oh, to achieve a PWM MS. And then for the same thing, for this thing, we just use this is really easy to find from the AR. That's the.
The timers.
It's literally just what you move. This killer, right? That's alright. Like, what do we change it to? No arbitrary.
Error? Do you like?
So AR is your at appearance, right?
So I guess like
How many times as many hertz? 2,000, 2 kilohertz.
So, I don't know. Choose one thing, so it's 0 to measure.
What's your
Between your period and your AR.
So like it depends on
Yeah, calculation. Unless we're
Correct.
Matter what.
I don't, let's see, this is the rising edge here, is that where an event hurt, and that's this is the rising edge of this clock, rising edge of that clock.
It's gonna be the period of this clock.
It's not the rising edge of this graph. So here we've gone to 3,
This clock.
something occurs, we've hit 3, something occurs. The moment 3 occurs. And that's just an example, I should have been clear, I can change this.
Yeah, I'm just hiding the counters large.
You're getting in 16 megahertz.
Sorry.
You want 100.
I made a mistake that will cause you all pain. This graph is just to remind you. So you didn't have to look back the other pages as you construct this. You can have a CRC that's bigger than 3, is other than 3. You can have an AR that's bigger than 6. It's a 16-bit timer. So this was just to help, and it didn't. All right, so
No pre-scaling.
Is it like what bounding? How much percent? So the prescaler adjusts by
milliseconds
Like
is.
LCD screen that can connect with.
Yeah, but in milliseconds, this 16 megahertz clock is 80,000. This it's. That's what like, if you're gonna have this, this is it.
Oh, I have a smile. 100.
Let me show you this.
thing down to what? What's your frequency then? Is that
This is where I'm confused.
I had 4 touchdowns.
What is 1/10 milliseconds?
I had 2 pick 6 touchdowns, and I had a third interception that I almost returned all the way.
It is a clock out.
Like a 10 to 20.
Yeah.
Seconds, so we need to convert that to.
Because like the way you can block in flag football, you can't.
It's just like
Anything over 2,
which is fine. I didn't tell you maybe to scale it, maybe your time scale very small
Yes.
or very long, right?
Yeah.
And so how many times do you have to count? How many counts do you have to do to get up to 1?
So what do you say? 100 equals.
just double guard him. And then just see megahertz. Yeah, like it should be.
This got like 15,000.
The whole timer is 16 minutes.
Touchdowns as well. Because we get high, like, I can throw it to anyone.
On doing that, you could.
This is counting once every.
The clock is 60 megahertz. I think we're fine with this, aren't we?
Timer's output is high.
It's greater than or equal to. For sure. Yeah.
Yes. Yes.
Megahertz.
16. Just be like a tiny little LCD something.
Makes way more sense to me to like do like yeah light.
Because it's 16 megahertz.
It's that makes sense and not like unreasonable.
Yeah, what's the highest number?
65,000.
Oh, so it's higher than
I set my PSC to be able to 16,000 because that would mean each clock cycle would be.
Yeah, my PSC is 15,000.
Error, can we find the error? Getting
PSC plus 1.
It is what I know.
I think like
I don't.
Somehow there's great effort.
Do you know what the clock outs come
And annotate their entire memo.
And also like my error is fine.
30 minutes each.
Does this look correct? So I have a PSC that is it's a quarter.
Like you can pre-scale it to whatever you
If you use the
But then apparently there's 2 other extra credits this year.
Yeah, or 5.
I mean, I can make it look PSC larger.
Well, yeah.
So I just did a duty as 1 over CCR.
Then it's like, then you can actually kind of notice the gap.
Just 2 times this.
But like if something blinks 1 out of every
2 megahertz clock.
oh yeah.
Bring that to seconds.
Yeah,
Good 5 seconds to milliseconds.
And then I also got a CCR of 5.
We're getting that now.
Oh, and I did.
One minus
Thank you.
How'd you get the period?
And you might.
Okay, 5. But that's
Okay, I think we're gonna pre-scale like 1599.
We have to divide the program
I can cross off.
cycles in half a millisecond. So we need to do
1599. What? You had a pre-scaler of 3.
one minus 1.
So I'm just gonna.
All right, so somebody want to tell us how they solved this problem? What period? Now, there's lots of periods you could choose, right? There's a trade-off between the period size. The prescaler will give you more or less steps. So there's one group that chose a very aggressive prescaler, which is fine. The questions didn't tell you anything, where you could only count basically in chunks of 1 millisecond, right? Which is fine, except if you later on you happen to want to do 11% duty cycle, then you wouldn't have the resolution anymore to go fine grain. So there's a trade-off, and there's multiple answers to this problem. So you might want to choose a prescaler that gives you enough gradations, enough counts up before you hit your ARR for your application. So can somebody just give me some answer that they came up with for a period? Or how do you approach this? Yeah.
I went to a period of 1/10 of a millisecond.
Okay.
And so the prescaler was 1,599.
Yeah.
And then ARR is 50 because you're counting up 100 or up 50 down 50.
Yep.
And then CCR is 45.
Okay, that all sounds about right. I didn't follow all the math in my head, but that sounds about right. Okay, so here's what I came up with. 3 formulas you got to figure out here. You got to figure out your clock, your period, and your duty cycle. So I just said prescaler of 15, which just took that 16 megahertz clock. You know, the prescaler formula means you always have to have that 1 extra. So I divide it by 16, give me a nice round number, 1 megahertz. And then I went through and figured out my AR was 5,000, and then CCR is 4,500, just to get through that. So this will be on the unredacted version if you want to follow this particular math. Any questions? Yeah.
How did you decide to make it 1 megahertz? Like, how did you know to start there rather than taking the numbers that they give us in the problem and trying to work like backwards, I guess?
There's multiple answers to this problem. That's one of the challenges. And so I could have done a 100 kilohertz clock. I could have done any values and just had it as long as they came up to having a duty cycle or a period of 1 millisecond and a duty cycle of 1 millisecond, or sorry, 10 millisecond period and duty cycle of 1 period. So there's multiple answers. Does that unsatisfactory answer your question? Okay. And again, the trade-off is just, I guess there's two trade-offs. What's the resolution you want in that duty cycle? That would be one trade-off. If you wanted to have really fine resolution, you probably wouldn't do a prescaler that's so aggressive. And another one might be, what else are you trying to do on this clock? So maybe you choose a period because you have some LEDs, you have multiple servos with different timing requirements. You try to figure out the best period for that. And then you're choosing different CCRs for different duty cycles, yeah.
So like theoretically, you didn't even have to have a prescaler?
I think you could get away with this without having a prescaler. I don't know if I made the problem evil so that you couldn't get to 1 millisecond. I think you can get to 1 millisecond. It might not, the math might not come out perfectly so you get that 10 milliseconds.
Is that supposed to be PSC and it's not, right?
PSC, PRC, PSC, yeah, okay. Ooh. Can edit that in real time. It would be easier if I could do this for tests. When me and Matt make mistakes. Thank you. Yeah.
I don't understand why the formula in there is different from the formula in the pre-lab.
In the pre-lab?
Yeah.
What's the formula in the pre-lab?
It says that the PWM period is 1 plus ARR times 1 over the clock frequency.
Yep. We went over it quickly. You may have not fully gotten it. Let's see. So when you're doing triangle waves, it's AR plus 1. And you can just count yourself up. It's actually 7 steps up, right? And so that's why it's AR plus 1. But if you go up and down count, then you don't have that plus 1. I don't know why. You can count yourself through this little problem and prove it to yourself that when you're going up and down, it's not plus 1.
Okay.
So it's a horrible one-off, just remember it fact.
Sure.
Can you go back to the the 1 megahertz that you get?
Yep.
Is that for the AR, the PWM equals 2 times ARR times timer clock period? Like, where are you subbing in that 1?
So 1 over your frequency is going to give you your period, right?
But is it for, are you putting it in for timer clock frequency?
Timer clock period.
Would we be expected to know these formulas for any future exam?
Yeah. Some of them I kind of think about as brute force knowledge. Like, if you have a prescaler, you divide it by some value, change the clock, right? And now you have to remember that there's a plus 1. Oh my gosh, you may have forgotten that this particular architecture forces you to have an offset by 1. So typically in a test situation, I'm not going to kill you because you're off by 1. In fact, sometimes if the number is really large, you can't even tell. Like, get on an oscilloscope and try to measure you're off by 1 clock cycle might actually be hard. So I try not to kill you on the little idiosyncrasies of this particular architecture. But yeah, you should be able, if I give you, make me a pulse width modulation like this, you should be able, and here's your clock, you should be able to solve those things. Any other questions? Yeah?
I thought that we were given that we want like a period of 10 milliseconds.
Yeah.
And like, so my all calculations were like 15,999 because of that.
I'm sorry?
So like, if you, instead of the PSC formula, like if you work with having like a 10 millisecond time period, so you get like weird large numbers with like, you have 16 megahertz minus 1, and then like, I'm just confused that like, is the catch here to like find a clock period, like do we, like finding a clock with like 1 megahertz instead of like reading exactly what was on the sheet and like trying to work that way through?
Well, I think the challenge is there's multiple answers to this question.
Okay.
Right? So I could have chosen to have a 1 megahertz prescale clock. I could have 100 kilohertz. I could have had 3.5 megahertz. I could have had any weird value I wanted for my prescaled thing, as long as the AAR and CCR came out to giving me a period of 10 milliseconds and a period of, or a pulse width of 1 millisecond. So I think that's the challenge. There's no inherently right answer. There's a line of right answers. All right, yeah.
I was just curious if people like the STM people, if when they make a data sheet, if they include these formulas, or they just expect like engineers to figure out like what the period would be and make an equation.
They're going to tell you this because there's no way for you to know there's a +1. In fact, I remember that in there. They may explicitly, I feel like that's more the level of a tutorial. Like a data sheet would be, or an application note. A data sheet just tells you, this is the functionality. These registers do this. Good luck. But they know they exist. And then a tutorial or application might know, I bet there is one for timers for the STM32. It might give you concrete examples. So that's just a good thing, like knowing where to find information about your engineering project, whatever it is, whether it's some library or some manufacturer part. There's a difference between what data sheets give, what application notes, what a YouTube tutorial gives. Like there's just all these different levels of information, and it's important to be able to find your information you need. What else? Any last questions? Okay. All right, so yeah. All right, so at this point, through timers, you've learned about oscillators and how we take something from the physical world, this crystal oscillator, and we get different clocks. And it's generally important to know low frequency clocks, what they're for, why you would use one, high frequency clocks. The internal oscillators are very nice because you can digitally control them. So you can change your clock on the fly if you wanted to. It just might not be as precise as you want. PLLs are a more expensive way to do it, and you can also change those on the fly. But it's just good to know that there's generally clocking options. If you go look through Cube IDE, you get to see this clock distribution tree that you can select from. Really what you guys care about is probably just the prescaler. That's the thing for the timer modules that you'll need to change. You have capture and compare timer registers. So capture is you're trying to measure things from the external world. Start a time, and then when some external event occurs, lock the current time in my register or my counter into a register for me to look up later. And now you know what was say you're trying to measure a pulse width coming in. You could say, start when the period goes high, and then when the thing goes low, capture this value, and now you could measure a pulse width modulation. Compare is how you generate these pulse width modulations, or just compare 2 times and have an event go off. So it could literally just be a timer, start here, wake up the core after so many counts, and then some activity is going to happen. And we talked about a bunch of pulse width modulation stuff. All right, I think we'll have, well, talk a little bit about this. But we want to talk about virtual timers, just so you guys have a concept of it. This helps when if you go to 473, you're going to be talking about RTOS. And virtual timers are an important part of RTOS, which is a real-time operating system. If I had done this lecture cold, I would have reminded you what these 2 things are, which are just capture and compare timers, and that there's multiple of them. I guess take a moment, work together, and say I have a 100 megahertz clock. What's the maximum amount of time that I can measure what these things are, right? So kind of very related to what you just did, but if you have a 16-bit timer, what's the maximum time you can time for 32-bit and 64? So take a couple of minutes, work together.
I guess
Yeah, do it on the back, that's fine. I'm not gonna, well, it's not like a graded projector, but just for you guys to think about.
Would it just be like 100
Just have some input right now.
like define it. Remember, it's recording. It's gonna get so much bigger. There's back about 2050.
timers, right? Just be a brand new one. That times your period.
Because they have so much space.
Well, I have a formula here.
I'm kind of the same though. Assuming we can have a 16-bit person.
That's why you only have like
Have a 16-bit
or something, you know.
The maximum.
16 bits.
The max number.
And you know that off the top of your head.
No, I looked at
It's 2 to the 16.
2 to the 16 minus 1.
Obviously, that's, I am doing the correct logic though, right?
And that would, you just multiply that by the number of what it takes to do a single cycle.
Yeah, I think you just divide like
How long
2
each
to
of
the
those
minus 1 by the time period.
Doing like nothing in that area, this area.
I wonder if he wants us to consider the fact that we can, if we're doing count up that overflow, count down that overflow, or count and then down. Yeah.
One full cycle.
Yeah, one full.
Whatever the band left separation store.
Either way,
16
it's
or 16.
Two
That's the unique things you can have, right? So that's like that times
16
your.
with the minus 1.
2 to 15. Then minus 1. Oh, you're right.
I know this is mostly this.
That's what I can
To
do.
get it into your laptop.
Really bad though. I touched this, not this.
It would be really cool. So the fact that it's not.
Is it hard? Lightweight.
I want a T89.
It's a one to carry around.
It is.
For 16.
650 microseconds.
What about 64?
Kind of, yeah. We suffered 260 together.
Next Monday.
Some of them are part.
My class is my good friends.
Very true.
All right, so what are we going to get for 16 bits? What's the largest time? You have a timer that's going with a 100 megahertz clock. What's the largest time you can count up to? It's a 16-bit timer.
Seconds.
Yeah, 60, yeah, same thing. 6.655 milliseconds or so. What about 32-bit timers? Or counters, sorry.
9 seconds. I said this earlier.
Okay. Now I know somebody else on this side of the room has a different answer. What about 64?
Like roughly 5.8 thousand years.
If we just put 64-bit timers everywhere, that would be real easy. But the reality is it's pretty rare to have 64-bit timers, at least on 16-bit or 32-bit architectures. I think almost all the timers you have, your devices are 16-bit timers. There may be a 32-bit device, 32-bit timer. I can't remember if it's this or Smart Fusion that has that option, or your particular Nucleo has that option. But basically, there's just a dramatic difference, right? And this is just a logarithmic power. Okay? So, given this constraint that there is a hardware constraint, and then larger timers have larger powers, all these sort of things, we're going to have to work with smaller timers and to do longer tasks. So somebody asked about how do we measure things that are really long in time, and so that's where virtual timers come in. And so we'll talk about virtual timers a little bit, and then we'll wrap up for the day. Okay. So, question is, how many timers are enough? Yeah.
Sorry, just like set up one of like those. I think I still just didn't really get like how 665 milliseconds.
Well, let's see. So what's the largest? So what's the number? 16 bits. So 2 to the 16 is some value, right?
Yeah.
That times the period So 1 over 100 megahertz is the clock period. So that times 2 to the 16th gives you some value there. I think that math works. Yeah? No?
I don't believe it.
You don't believe it? How many people believe the 32-bit value?
Isn't 2 to the 32 like 4 billion? And then isn't 100 times 10 to the negative 6 also? Oh. I see that.
I like. See, this is also what I do in exams. Where you're like, oh, half the class believes that my answers are wrong. Okay, I better go check.
Can you count up and down to double the periods?
You could. One clever person over here said, aha, I'll use what you just taught me against you. Could it do that? You could also use a prescaler. We just didn't give you those options in this problem. It was really to think about, force you to do a little bit of math, but also think about the time scales here and kind of motivate that if I want to look at anything longer than 42 seconds, or even in the STM's case, half a millisecond, we're going to have to do something else. Now, we're running out of time. All right. Any other questions? All right. So the answer is there enough timers? Almost never enough. Almost always, there's never enough timers. You can always go up in bigger and bigger classes of chips. It's just that you find that the number of things you have to keep track of or control is somewhat limited. And so you may find that you need more timers, especially for really long things. And so how do you deal with that? You make software to handle this. So why don't you talk to each other for 60 seconds and come up, what is the algorithm that you would come up with to make yourself a way to have timers that go really long? So you have a small timer, but you want to virtualize this or use software to make that timer very long. And how would you deal with multiple events at once? So just brainstorm for a second, come up with an idea, and I'll tell you how some people do it.
Two 32-bit timers at the same time.
The increments every time multiply that by.
Oh, this is
botanical process. You never need to clear that
This is like
All right, so what are some possible ways to keep track of multiple long-term events? I know you're talking to each other. It could have been about this class.
like when the timer reaches the timeout, you like make an interrupt and then handle increase in time.
You just have like a software counter essentially that counts how many times that things have been around. It works great. What happens if you have multiple events you're trying to keep track of?
Whenever like the counter reaches a certain threshold.
I think that's right. All right, so what you're saying, let me rephrase and maybe I'll reinterpret. What you're saying is you have a counter that's going off, you have the timer that goes off, and then in that interrupt service routine, you could be keeping track of multiple tasks that you need to, or events that you need to time. Is that? Nope, that was not what he was saying at all. Okay, well sorry, if you can elaborate more if you want, but maybe that's what I got out of it. So the simple idea is, say you have 13 or a number of events here. So in 10 seconds, something has to happen. In 13 seconds, in 20 seconds, in 43 seconds, something has to happen. So you could go and set up your timer to go off for 10 seconds, and then your ISR goes off. And then you have a list of events. And so this one went off, okay, so you do a task. And then you know that 10 seconds has gone past since that last interrupt went off. So then you go and take 10, subtract from 13, you have 3 seconds into your next event. Set your next event here, or next one was 20, 10 have gone past, so there's 10 seconds left. Your other fourth event was 43 seconds, and then there's been 10 seconds past, so 33 seconds to go. And then that's what you do in your interrupt routine. And then you go and say, okay, timer, count up to 3 seconds, or whatever it's capable, or in this case, 3 seconds. Let's assume your timer's capable of that. And then you go through, you wake up, your interrupt goes off. You go, okay, do the task, whatever the 3-second timer, that thing's elapsed, and you just take 3 seconds off the rest of your event. You just keep on decrementing until all your timed events have been extinguished. So go 7, and then you have 23 seconds left. Yeah.
Do you also take off the time that it took to perform the interrupt?
Ooh, now that is a tricky question. So interrupts, we know it takes about 12 cycles to get in if there is no bad memory hits. And there could have been, and you have a pipeline processor as well, so you could lose some of your stages of pipeline. So I just point out that if you care about really fast things or really precise things like 12 cycles, you probably don't want to use a virtual timer. The virtual timers are good for things in seconds, not milliseconds, or it's not microseconds. Could be good for milliseconds. All right, so let's walk through an example. So in this example, what do we have? We have a counter. We have some program that's going to set up your counter to some value, and it will cause an interrupt that will do something. So there's a timer module. It has a count that's going to go to some value, and an interrupt is going to fire. In this toy example, we'll have multiple tasks that need to get done. So program 1 wants a timer to go off in 3 minutes. Program 1 wants something 5 minutes. Here we have program 2 has a delta timer or a repeating timer. So every 2 minutes something should happen. Program 3 every 7 minutes, and in 4 minutes program 4 wants a timer to go off. So that's the requests that are going to occur. Then let's see. Then you've got some virtual timer code that needs to do some tasks. So you have a virtual event queue. So you need to update the queue and adjust the time. And then your ISR is going to do a task. So your ISR is going to go off like we talked about, and it's going to figure out what is the thing that look at the queue, what's the thing that's at the front of the queue, that's the thing that caused the timer to go off, and then it has a bunch of other, it has to decrement these tasks, as we'll see in a minute, and it has a bunch of other tasks to do. All right, so let's go through an example here. So here, we got to go make a list. So this could be a double linked list. We have a timer. We're going to go through our program, and our program is going to add events. So it's saying in 3 minutes, this is not repeating timer, in 3 minutes, have something go off. Okay, and then we're going to set our timer, hardware timer. In 3 minutes, I want you to send me an interrupt. We're going to add something to this list. Here we have a 5-minute that timer should go off. Here we have a 2-minute timer. This is the current amount of time on the timer that is required for it to go off, and then it's going to repeat every two minutes. And in this particular case, you would have to resort because 2 minutes will happen before the 3 minutes. So you're going to have to put this at the front of your list. And then you keep on adding elements. You put the 7-minute on, the 4-minute, but you need an ordered list, as we'll see in a second. So you reorder, and now we're ready to go. So we have a list of all the events that need to occur, lowest first, of the events that should happen. And now we're going to set our timer to 2. We're going to start decrementing. Go to 1, and then the timer goes off. So it triggers an interrupt. There you go. Well, figure out what the source needs. So the source is a delta timer. So we're going to go up. We're going to decrement all the other values. So this timer used to be 3. Now this has gone to, so the green box there was 3, but 2 minutes have already gone off. So the current amount of time left for that timer is 1, and all of those have been decremented. So we're going to update the times. If there's new events, we'd insert them, and then we're going to start the new timer. What's the value of the new timer? It's going to be 1 because that's the timer at the head there. Okay, we're going to go through, set the timer to 1, go off, do this task. The interrupt goes off. We're gonna service this one. It's not gonna be repeating. We don't have to put it back in the stack. We're gonna update all the timers and keep going through. So basically, you're just looping through these events, this list, until your events have been done. What we didn't talk about is what happens if a new event occurs. So say your program says, I want a new timer. Well, then it just stops the timer wherever it is. It goes and decrements, it stops the timer at that point, decrements all the rest of the events, the appropriate amount, resorts the list with a new thing, and then it goes forward with the remaining amount of time on the timer. I know that was super quick. It's just supposed to be an overview of how a virtual timer would work and how you can have interrupts and one timer control multiple things. This is for longer term events, not precise microsecond timing. All right. We'll have some office hours after class today for half an hour if anybody would like to ask questions. I assume this room is going to be, oh, please hand in your worksheets. I assume this room will be busy. We'll go up to my office.